Hello everyone, this is lecture 9 of the subject analog circuits, and in this class I am going to discuss the different configurations of MOSFET. Actually, we are going to continue with the different configurations of MOSFET. In the last lecture, that is lecture 8, I had discussed the first configuration of MOSFET, that is common source amplifier. So, in common source amplifier, we had derived the expression of output resistance, voltage gain, and of course, the input resistance is infinite in case of MOSFET. And we had considered that common source amplifier without source resistance. Now, in this class, we are going to learn common source amplifier with source resistance, without source resistance, we had already done in the last class, and after that common gate amplifier and common drain amplifier. So, in lecture 5 and in lecture 6, I had discussed common emitter amplifier, common base amplifier, common collector amplifier in BJT. So, I will suggest that before doing this, you can firstly go through those lectures, firstly study common emitter, common base, common collector. It will be easier to understand the MOSFET part also, because many things are similar, fine. So, starting with this common source amplifier with source resistance, and after that common gate and common drain amplifier, and of course, what we are going to do? We are going to calculate the input resistance, not input resistance, in fact, in case of common drain amplifier and in common source amplifier, since the input is applied at the gate terminal. So, your input resistance is 0, because we consider that gate current is 0, because there is a SiO2 layer, insulator layer, right. So, but in case of common gate amplifier, we will see that what is the input resistance, fine. So, starting with the common source amplifier with source resistance. So, I have already discussed that in different configurations where we apply the input, from where we take the output, fine. Like in common source amplifier, we apply the input signal at the gate terminal and we take the output from the drain terminal. And we have assumed that all the capacitors, external capacitors, that is coupling capacitor CC1, CC2 and your bypass capacitor CS. We have considered these capacitors as to be short circuit, to be acting as a perfect short circuit. So, we have neglected the effect of these capacitors, that is why in this circuit there is no capacitor, that is the first thing. And of course, to derive the equation for voltage gain, output resistance, we have to draw the small signal model, that I have already covered. In a small signal model, we can draw the hybrid pi model, T model, we can draw any model, but if there is a resistance at the source terminal or resistance at the emitter terminal in the BJT, then T model is preferred, because it is more convenient in case of T model to derive the expression if there is a resistor connected at source, although we can draw the hybrid pi model also. So, this circuit is the small signal model of common source amplifier. Now, you can see that to draw the small signal model, we remove all the DC sources, like DC voltage source, we short circuited it, and current source is open circuit, fine. Voltage source is short circuited and current source is open circuited, fine. So, that is why there is no DC quantity in this small signal model. Now, you can see that this gate current is 0 and the resistance appear at the source terminal of the MOSFET, that is 1 by Gm. RS is your external resistor which we have connected externally, and of course, we are considering the discrete circuit case, and the purpose of this RS, we know that it provides negative feedback, I had discussed it in the biasing of MOSFET. This is your dependent source, fine, and RD is the drain resistance. The one terminal of the RD is connected to the VDD. So, VDD is removed, that is short circuited, fine, that is why the one terminal of the RD is grounded. Now, we have to calculate the voltage gain, that is we are going to calculate the value of V naught upon Vi from this small signal T model. The input resistance is 0, you can see that the gate current is 0. If the gate current is 0, so it means that if we apply the signal at the gate terminal, then the input resistance will be infinite, Rn is infinite here. Now, see from this small signal model how we calculate it. What will be the value of VGS here, gate to source voltage, that is with the help of voltage division rule we can calculate it. This is your Vi. So, VGS will be Vi into 1 by Gm upon total resistance, fine, voltage division rule, same branch upon total, fine. So, 1 by Gm upon 1 by Gm plus Rs. So, it can be written as Vi upon 1 plus Gm Rs. Now, what is the value of the output voltage? We have done it earlier also, since the direction of the current is opposite. So, you can calculate it, this V naught, it will be minus I into Rd because of the opposite direction. So, V naught is minus I into Rd, and what is the value of I? You can calculate it here. The value of I, that is flowing through 1 by Gm resistor and Rs, the value of I, it will be the voltage Vi upon the total resistance. The total resistance appears here is 1 by Gm plus Rs, fine. Now, this I you can put here in this equation and you can get the relation between V naught and Vi, very simple, fine. Now, just put the value of I in this particular equation, that is V naught is equal to minus I into Rd, and rearrange the terms, then we get V naught upon Vi, that is equal to minus, there is a minus sign, minus of Rd upon 1 plus Gm plus Rs. Now, this minus sign is coming because it is a common source amplifier, like in the earlier case also, in common source amplifier without source resistance the voltage gain was negative. So, negative gain means output is 180 degree out of phase with input. Now, you can see one more thing, the voltage gain from gate to drain, actually the voltage gain it will be from gate to drain because we are applying the input at the gate terminal and we are taking the output from the drain terminal. So, the voltage gain you can see from this expression, it is the total resistance in the drain, that total resistance in the drain is Rd and the total resistance in the source, the total resistance in the source is 1 by Gm plus Rs, that is the voltage gain. Now, just if Gm comes in numerator, then it is minus Gm Rd upon 1 plus Gm Rs. Now, there is one important conclusion is without source resistance the gain was minus Gm into Rd. Without source resistance the voltage gain which we had find out in the last class, that is minus Gm into Rd, but with source resistance it is reduced by the factor 1 plus Gm Rs. So, that is the drawback of source resistance Rs that we have connected at the source terminal. The drawback is the voltage gain is reduced by the factor 1 plus Gm Rs, that we had seen in the common emitter amplifier with the emitter resistance also, but the advantage is this Rs, it provides negative feedback that stabilizes the drain current, fine, that is important. Now, we can calculate the voltage gain considering the load resistance. This AV naught is the open circuit voltage gain, AV is the voltage gain considering the load resistance. Now, we can get this expression AV is equal to minus Gm Rd parallel to RL. So, it is very similar. If we are connecting RL, then that RL will appear in parallel with Rd. That is why in the expression of AV naught just put Rd instead of Rd, just put Rd parallel to RL, fine. Now, What will be the output resistance? Output resistance, we find out that output resistance by putting the input signal source is equal to 0, then you can see that the output resistance is simply R d. In case of common emitter amplifier, we had got it R c, that is the resistance connected at the collector. Here the resistance connected at the drain, that is your output resistance, fine. Now, next case is common gate amplifier. So, in common gate amplifier, we apply the input at the source terminal, since the gate is common, gate is grounded, and we take the output from the drain terminal, fine. And V sig is the input signal source and R sig is the internal resistance of the input signal source. And again, considering that all the coupling capacitors are acting as a perfect short circuit, that is why there is no capacitor involved in this circuit, and but there is a resistor at the source terminal. So, T model is preferred, T model will be preferred, that is why we have drawn the T model of this common gate amplifier. You can see that your gate terminal is grounded, your input signal is applied at the source terminal, right. This 1 by G m is the source resistance, R d is the drain resistance, this is the dependent source. You all are familiar with it because we have done it multiple times. So, you can see that the input resistance from the T model, it is a very straightforward. The input resistance is 1 by G m, the input resistance is 1 by G m. See, in case of common source amplifier, the input resistance is infinite because we are applying the input at the gate. So, we get more input resistance. Input resistance is infinite is the ideal case, right. Practically it is in mega ohm range, but it is very high. But in case of common gate, the input resistance is only 1 by G m. That is the problem with the common gate amplifier. The input resistance is less in case of common gate amplifier. That is why when we design any voltage amplifier, we do not prefer this common gate amplifier, because for any voltage amplifier the input resistance should be high, it should be high in order to avoid the signal loss. So, it is not preferred, but there are applications of common gate that I will discuss later. Now, see, you can calculate the V naught again like we had done in the earlier case. Now, we can find out the value of I here. What is I? The current flowing through 1 by G m, that will be the current I will be V I upon 1 by G m with minus sign. This is I, just put this I in this equation, that is V naught is equal to minus I into R d, and just evaluate, just calculate V naught upon V I, and of course, this V naught upon V I is the open circuit voltage gain. Open circuit voltage gain means we have put the load resistance is equal to infinite, fine. So, you can see that the open circuit voltage gain is G m into R d. So, it is similar to the common source amplifier without source resistance that we had calculated in the last class, common source amplifier without source resistance. In that case, the gain that we got was minus G m into R d, here we are getting plus G m into R d. So, the magnitude of the common source, magnitude of the voltage gain of the common source without source resistance is equal to common gate magnitude, not sign. So, this common gate amplifier, it is a non-inverting amplifier because output is in phase with input. In phase, why in phase? Because the voltage gain is positive, but in case of common source amplifier, that is your inverting amplifier. Inverting amplifier means output is 180 degree out of phase with input, because in common source amplifier we are getting the negative gain. Negative, do not be confused with the negative sign, it just represents the phase shift of 180 degree, and again R naught will be equal to R d. To calculate R naught, just remove the input signal source, and you can see that very straightforward, your output resistance is R d. And similarly, we can calculate the overall voltage gain. So, overall voltage gain, it is defined as V naught upon V sig. We have already calculated it for common base amplifier, for common source amplifier without source resistance. So, you can calculate it V naught upon V sig, fine. It is very easy, we know the value of V naught upon V I. Now, there is a relation between V I and V sig that you can find out with the help of voltage divider and just find out V naught upon V sig. Simple mathematics, you can do it, we have already done it in common base. So, similarly you can do it for common gate also. So, you can see that the overall voltage gain it is again simply the ratio of the total resistance in the drain circuit, that is R D parallel to R L, if we are considering this R L, and the total resistance in the source circuit, that is now it is R sig plus 1 by G M. R sig is the internal resistance of the input signal source, 1 by G M is the source resistance. Because of its low input resistance we are saying it because the the input resistance which we are getting for common gate amplifier is 1 by G M, that is small. It is very limited applications, but there are some applications of common gate. The first is we can combine common gate with common source in order to enhance the performance of the overall circuit, that is the cascode amplifier that I will discuss in unit 2. Cascode is the combination of common source and common gate. So, that cascode it combines the advantages of common source and common gate, fine. Now, that is one application, and another application is since the input resistance is very less in case of common gate. So, common gate is of course, it is not preferred for voltage amplifier, but in coaxial cable like I had discussed in the common base amplifier, you can refer that class. So, in coaxial cables what happens, the characteristic impedance of the coaxial cable it is very small, that is in the range of 50 ohm to 75 ohm, fine. So, we need the low input resistance there, because that input resistance should be matched with that characteristic impedance of the coaxial cable. It should be matched, right, in order to avoid the signal reflection, because if there is a signal reflection there will be loss, signal loss, that is not acceptable at all, fine. So, low input resistance we require because the characteristic impedance is very less in coaxial cable. So, the low input resistance we are getting from which configuration? From common gate, because in common source and in common drain we are applying the input at the gate. So, the input resistance is high. So, that is the one another application of common gate, that is in cables, fine, and it is having excellent high frequency response because there is no Miller effect. It is having excellent high frequency response in comparison with common source amplifier, because in common source there is a Miller effect, there is no Miller effect in common gate. So, I will discuss this Miller effect in further classes when I will discuss the frequency response of common source amplifier, fine. Next is your common drain amplifier, it is very similar to your common collector in BJT. So, in common drain amplifier we apply the input at the gate and we take the output from the source, since the drain is common. So, this common drain amplifier, just review common collector amplifier that acts as a voltage buffer. Similarly, this common drain amplifier it acts as a voltage buffer or voltage follower, and second thing is this common drain amplifier it is also called source follower. It is a very popular name, like common collector configuration, common collector amplifier it is called emitter follower, common drain is called source follower. The reason is very clear, because this common drain amplifier it acts as a voltage buffer. So, your voltage gain is approximately 1. So, whatever input we apply at the gate terminal the same appears at the source terminal. So, your source voltage is following the gate voltage, that is why it is called source follower. So, the question arises that if whatever input we are applying, if we are getting the same thing at the output, then what is the need of such circuit? We can understand this need from this diagram. Suppose that if we have a input signal source and the internal resistance of the input signal source is very high, it is 1 mega ohm, and we have connected this signal source, input signal source with a load resistance of lower value, that is 1 kilo ohm. Then what happens? Suppose that if we have applied 1 volt signal at the input, then what will be the voltage appeared across the load resistance? You can calculate it, just find out the current in this loop, then find out that what is the voltage drop across this R sig, then the remaining voltage will appear across load resistance R, then you can find out very easily. So, after doing this, when we are applying 1 volt at the input, then what voltage we are getting at the output, that means across the load resistance R L, that is only 1 millivolt, only 1 millivolt. Is it acceptable? Absolutely, it is not acceptable. We are applying 1 volt input and we are getting only 1 millivolt. Huge signal loss, huge signal loss. So, to avoid this signal loss, what we do? We connect a voltage buffer in between the high resistance source and low resistance load, between high resistance source and low resistance load. So, how this voltage buffer removes the problem of this signal loss? Since the input resistance is very high, obviously the input resistance of common drain is very high, because in common drain amplifier, I keep repeating it, the input is applied at the gate and the output is taken from the source, fine. So, whenever we apply input at the gate, then input resistance will be high, fine. So, it is in fact infinite, but practically it is in mega ohm range and the output resistance is very low. So, again if you calculate in this loop, apply the KVL and just calculate that what is the output voltage, that is the voltage appearing across load resistance R L, then it comes to be 0.9 volt. Now, we are applying 1 volt, we are getting 0.9 volt, although there is a signal loss of 0.1 volt here, but that signal loss, the factor by which the signal loss was appearing in the above case, now it is reduced. Without voltage buffer, we are getting only 1 millivolt from 1 volt, but in case of voltage buffer, using voltage buffer, we are getting 0.9 volt. So, the purpose of this voltage buffer is to avoid the signal loss. We say that this is impedance matching. We do not connect high resistance source with low resistance load directly. If we connect it, then there will be the signal loss that I have explained. So, to avoid the signal loss, we need to connect that voltage buffer in between high resistance source and low resistance load, fine. That is the purpose of voltage buffer. Now, again we have to calculate the input resistance, output resistance and voltage gain. Input resistance is very much clear, because the input gate current is 0. So, the input resistance is infinite, fine. Now, you can see that the input is applied at the gate terminal and the output is taken from the source terminal. Since there is a resistor involved at the source terminal, so it is better to draw the T model, fine. So, we have done it earlier also in common collector configuration. So, all the things are same, only the device has changed. There we had taken BJT, here it is MOSFET. There is some base current, obviously the base current in the BJT is low, but here we are considering that gate current is 0. See, the gate current is 0 because of that insulator layer, fine. That is the difference. Otherwise, the remaining steps to calculate the value of the output resistance and voltage gain, it is similar to your common collector that I had discussed in lecture 6. Now, see, this is the just summary of comparison chart of the common source amplifier. First case, this is your common source without source resistance. Next is common source with source resistance. Next one is common gate, and the last one is source follower. That source follower is your common drain amplifier. Now, you can see that the input resistance of the common source amplifier and source follower, that is common drain, is infinite, right. Why? Because the input is applied at the gate and the gate current is 0. But in case of common gate, you can see that the input resistance is 1 by Gm, that is very low, that I have discussed, right. And you can see the open circuit voltage gain for common source amplifier without source resistance, it is minus Gm into Rd, and with source resistance the voltage gain is reduced by the factor 1 plus Gm Rs. That is the issue with the Rs, but that Rs provides negative feedback, that stabilizes the circuit, that stabilizes your drain current, that is very important for amplification. And in common source there is a negative sign means output is 180 degree out of phase with input, that is why common source amplifier is the inverting amplifier. Common gate, you can see that the magnitude of the voltage gain is same as in common source, but with positive signs. So, common gate is your non inverting, output is in phase with input, and for source follower the open circuit voltage gain is 1, and the output resistance is, you can see that for common source and common gate it is R d, but for source follower it is very less. That is the advantage of common drain amplifier source follower circuit, the input resistance is very high, output resistance is very low. Now, these equations we have got for different configurations of MOSFET. AV is your voltage gain, GV is your overall voltage gain. AV we calculate, that is V naught upon Vi, and GV is your V naught upon Vc. So, we have done enough calculations for BJT and also for MOSFET. So, this is just the comparison chart of the different configuration, different MOSFET amplifiers. Fine. So, the conclusion is when we want to design voltage amplifier, we go for common source. Fine. For high frequency applications, common gate is preferred, and to design a voltage buffer for impedance matching in order to avoid the signal loss, common drain configuration is selected. This is the reference. Thank you.